universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to Sky Tour Radio here on KGRA Radio and KGRADB.com. How are you all doing tonight? It's a wonderful night. We've been having a great time both here in the East and in the West. Tara down there is down in the West, down in Arizona. How are you down there?
Great. It's a nice rainy day here. Loving it.
Some people love the rain, especially when they don't get any.
Right.
But your monsoon season should have been over by now, shouldn't it?
The end of this month, I believe.
Okay. So it goes into September. I thought it was July and August. But
I think it's September 30th, I think.
Really? So it's September 30th?
It goes by a calendar.
Okay. So by September 30th, all the clouds have to go away.
Yeah.
We wanted here. We got to leave.
That's right. They understand that.
That's right.
Apparently it works, too.
It does. And over there, we have Amanda. Hi, Amanda. How are you?
Hi, Mark. I'm well. How are you?
I'm just fine, thank you. And down there in the corner, we have Daryl. What's up down there, brother?
Hey, Mark.
Yeah? How are you?
I'm nominal, thank you. Warp engines are online.
Nominal. I love that. Nominal is a wonderful word because it's like you don't know whether it's actually really good or just okay.
Well, some people think it means marginal, but it's not. I mean, hey, warp engines are online. I'm ready to go.
That's right. Warp engines online, It's like, Scotty, ahead, warp factor 1, Sure. So anyway, I have my water so I can talk a lot tonight, but I'm not planning on it. I hope I can keep myself quiet. But I want to welcome you guys to Sky Tour Radio here. It is a wonderful September 26th, 2021. And I just wanted to share with you, if you don't know this already, is that Sky Tour Radio is actually Sky Tour kind of TV, isn't it? I mean, because look, hi, here we are. We're all here. Wave, Tara, come on, wave. See? Yeah, see, we're all here. Daryl and Amanda, they don't want to wave, and that's okay.
They're waving.
They are silently, that's fine. But
I don't want to break the camera.
Okay. Then what's my excuse?
I used to be so pretty.
Well, I find that to be hilarious because, we all add to the world in our own ways, some good, some not so good. But all of us here, we're adding in a good way. This one over here, yeah, you, Commander. She manages all things StreamYard, all the things that keep us live on the air, like you see us right here. Okay, Tara down there, she asks questions that are far and away the most perplexing sometimes and the most intriguing. And so she's going to be doing that tonight, too. You know that, right? You have a few that you're going to ask, yeah. And then Daryl, he adds these amazing vistas of the universe by going in and doing, we call it Deep Dive with Daryl. Okay, so we have Tara's Cosmos and we have Deep Dive with Daryl. And what he does is he actually dives into several constellations in the night sky and shares with us the deep mysteries of these stars. He'll sometimes talk about culture. He'll sometimes talk about things that are coming up in the night sky. Like right now when the sun sets, we have some cosmic interlopers out there that he might talk about tonight. And then when it comes to me, I guess I don't know what I do. I don't know. I talk a lot, but the truth is, astronomy is my bag, and so I tend to talk about the technical aspects of astronomy, in ways that I think are important for people to hear, but in a way that everyone can understand. It's kind of hard. Daryl's got that gift as well. We've both done presentations to the public, for many years. I still do. And so it's you have to tailor everything you say to the audience you're speaking to. And it's probably an important thing to make sure that you say things in a way that they can understand, or else they're just going to be, what, is he done yet? That kind of thing. And we don't hope that doesn't happen here, but And I gotta say, in the beginning, when this one was asking questions in the beginning, yes, you down there rubbing your nose, okay, when she was asking questions in the beginning, they were kind of simpler questions. But you know what? She's kicked it up about 10 notches. Now she's asking questions that are appropriate for, astrophysicists as well. And I'm really impressed with that. So we're going to hear what she has to surprise me with, or surprise all of us with tonight, because she's going to get to ask those questions. And if I don't know, I'm going to say, hey, Daryl, you want to take this one? I got to take a drink of water. But,
yeah, right.
Well, she's good. So, and Amanda will surprise you too from time to time when she adds her own 2 cents. She has a lot to say. And we've watched Amanda grow in her astronomy knowledge from a point where she knew nothing about astronomy, essentially, to being able to, as she will sometimes do, finish my sentences. If I delay the slightest bit, a nanosecond, she finishes the sentence with all the right data. I mean, I actually like that, because that eagerness and that interest is something that I have been trying to engender in everyone I talk to. So I think it's really cool to see someone who takes that on. I got to tell you a little story too. We had several weeks ago, we had the Pine Bush UFO Fair in Crawford, New York. And I was there with Richard Dolan and Lee Spiegel, and we all were speaking. But, we were selling our books and stuff like that. And, the book I have is called The Populated Universe. It's really a book that discusses the origins of life in the universe, here on Earth, starting with Earth and then expanding it out into the universe. And it talks about the search for life elsewhere. And, you sell books because that's what you do. You write a book, you want to sell it, right? Well, this little girl came up to me, and some of you might know this story already. And her name was Noah, N-O-A. Okay. And her mother looked at me almost, like trying to suggest that her daughter wouldn't be able to tell me anything I don't know, kind of a thing, and said, my daughter's been learning about black holes. And I went, really? I said, well, Noah, how are you? And she said she's great. And then she proceeded to, I asked her, well, tell me all about black holes. And this little girl, probably 10 years old or so, proceeded to absolutely astound me with her understanding of massive stars versus smaller stars like the sun, and which stars can become black holes, which can't, and how hot they are versus how cool some of them are. And halfway through what she was saying to me, I had already determined I'm giving her a free book. I cannot. This is she's earned it. And so I did. I wrote a nice little letter to it amounted to a letter in the front page of her book that I gave her. And she was very happy. And that harkens back to my first introduction into astronomy, when the man who's now the chief engineer at Jet Propulsion Laboratory was only a staff scientist down at NASA. And I had written a space station plan out, and I've told this story too many times. And the bottom line is, he read it. I sent it to him. He read it. And he actually took the time to make notations and write on each page of my little notebook paper space station plan. He took the time to write, good idea. We could do this. We like this idea too. And he checkmarked. Those little pencil check marks on each page were very, very important to me as a 9-year-old. I can't tell you why. I just know that means he read it. And then he sent me back, as I mentioned before, a giant box full of stuff. And that propelled me into astronomy headlong. And that's why when I tell you at age 9, I knew I was going into that field, that's the reason. And there was a secondary reason too. My parents got me a telescope because the chief of the fire department at the time, gave them the money to buy me a telescope. And I thought that was just the coolest thing. So together, those events shaped my life and made me become an astronomer, and as I say, this is what we look like. So the truth is, that was a life-changing event for me. So who knows, maybe giving her this book, it wasn't much. It's not a lot, but maybe that's enough to kick her over the edge into going into some of these sciences. And I think that would be a really cool thing. Who knows? 12 years from now, she might come up to me and say, do you remember that little girl you gave a book to? And I'd love to say, yeah. And I'd love to hear her say, that was me, and I'm an astronomer now. I mean, I'd love that, but who knows? It reminds me of another story too, when there were two Catholic nuns here at the house visiting, and they're relatives. And well, one of them is a relative, and this one relative brought her friend, and little white-haired old lady, nice, very demure, didn't say much, looked like a white-haired old lady. And you know what? Shame on me for thinking that this woman didn't know anything, because she said to me, you know, I hear the Hubble Space Telescope has some beautiful images. I said, oh, I can go print some out for you on my color printer. Would you like that? She goes, oh, absolutely. So I got the high gloss paper, and I really printed out photo quality 5 or 6 beautiful images taken by the Hubble Space Telescope. And I sat down with her at the table, and I began talking through all these things. Well, you know, this is a stellar nursery. Stars are made here. And what happens is the clouds of hydrogen gas condense from their own gravity. And she's nodding and nodding. Meanwhile, the other Catholic nun is starting to snicker. And I didn't know why. And I actually thought she was being rude. But I said, I can't think she's being rude because she's a Catholic nun. You know, I'm not religious, but, you know, I recognize and respect, you know. And I thought she was being kind of rude a little bit. But then I kept explaining more and more, and I talked about the chemistry of these stars. And that's when this other Catholic nun started to laugh out loud uncontrollably. I went, what? And she points at her friend sitting next to me, the little white-haired old lady, and says, she's an astrophysicist. What? And I found out that she was actually one of the people that was part of the team that landed for the first time in human history a probe on an asteroid that was near the Earth. It was called Near Earth Asteroid Rendezvous. And this little tiny person had the mind of a genius. And here I am thinking I can explain anything to her. I thought that was hilarious. And it was actually kind of cool. I did feel embarrassed. And I basically went, I'm not worthy, you know, and did the whole thing. Because I thought that what she did with the NEAR program was really quite spectacular. And I knew about it. I followed it. I had no idea that Sister Mary Ellen Murphy was the person on that team. So some years later, when she actually passed away, you know, which is too bad. We lost a good, science person there. The OSIRIS-REx probe to the asteroid was being sent out. And when I talked to the team, I said, I called a couple of folks on the team. I said, are you guys doing anything on, are you including microdots or any kind of imaging? And they said, well, yeah, go to this website and check it out. And I did. And they said, oh, well, do you have any photos of this Mary Ellen Murphy you'd like to include? I could, yes. So I included several photos. And right now she'll be orbiting the sun for, probably about 1 billion years. So she actually successfully got to the asteroid, and now she's in space forever. I thought that was cute.
That is cool.
That's awesome.
Your little girl story reminds me. May I tell a short story real quick?
Please do. I'm not the only one talking. Go for it.
Okay. Well, again, your little girl story reminded me. There used to be a kid, a big lunk of a blonde-headed kid that walked around my neighborhood a lot. He looked for all the world, I want to be nice here, but he looked like he was Down syndrome, okay? And I had the telescope out in the driveway one night, and as usual, if anybody walked by, they were free to come up and take a look. And he walked up, and he was really eager to look through the telescope. And I invited him up, and he looked. And then the kid, perhaps he was autistic, perhaps, and not Down syndrome, he went into the most amazing explanation of black holes I've ever heard from somebody his age. I mean, he just, again, he sounded like an astrophysicist or something. So that just amazed me and really set me back on my heels.
Isn't that crazy? And it's amazing. And there's so many gems out there like that. So many people know so much and say so little, and that surprises me all the time. It surprised me how much this one knew down here, that one right there. Yes, you, Tara. Okay. It surprised me how much this one here learned over the last several years. I knew about your capabilities, Daryl, and that's why you're here. Okay. We took a risk with her and it's paid off like crazy. And Amanda, of course, is indispensable for many reasons. But I've discovered that people know things. And the one thing I've learned is that science tends to be arrogant. And, just because we say we are science people, that kind of makes us sound like we're trying to set ourselves apart from everybody else. But guess what? Where I know science, I may lack I do lack other things. In fact, I lack a certain modicum of common sense, to be honest with you. I'm not the most sensible. And Tara knows exactly what I'm talking about. It has to do with my, desire to get the observatory built for everybody. I want to make sure that we all have an observatory to go look and go watch things and bring this science to people, bring it right to their doorstep, right on their big screens at night. And of course, I didn't even think about my well-being, and it almost did me.
Hydrate or die.
Mm-hmm.
Water everywhere, and not a drop he drank.
Not a drop I drank. That's a good way to put it. So as you see, I always have water with me. And I'll tell you this. When I 6 years ago, when I had the surgery that, of course, ended up causing me to be blind and have 8 strokes on the table, after that process, all I could dream of was drinking water again. I wanted ice water like you can't believe, but they wouldn't let me have it because none of this worked. I couldn't swallow. I couldn't move anything. The muscles were still dead, right? And luckily they came back. And I am missing a vocal cord. The vocal cord stopped working. So my voice is a lot deeper. A voice for radio, hey, I'm still not quite used to how deep my voice is, to be honest with you. It always sounds like I have a cold to me. Well, anyway, I wanted ice water in the worst way. And I remember this guy came in and he got down close to me. It's the only way I could actually tell someone was there because there was a gray shadow. And you know what's weird? You lose your sight, but you learn other things, okay? So this guy would come down to me and say something, so I knew it was a guy. And then I would smell. He had a smell to him. I don't know how else to put that. It sounds really kind of weird, okay? But you do make up for the senses. And I learned about his smell. And when he walked in, I could tell he was in the room. He didn't have to come near me. All right. And of course, I couldn't talk. I was intubated. And I just wanted to have ice water. Well, when they finally got the intubation, took out the tube, and now I could just have my regular, breathing myself. I asked for ice water. Of course, it didn't come out that way because I couldn't talk yet. It came out like, because I didn't know how to form words yet. Well, anyway, he actually gave me an ice chip on a little tiny sponge. And I can't tell you, I remember it to this day. Who would remember a stupid ice chip on a little sponge on a stick? I will. Because that was so incredible, that the taste. So when I look at ice water now, I look at it in a very, very different way, because the water is a miracle enough, right? 2 hydrogens and an oxygen, H2O, okay? And the ice, of course, is water that's in a frozen state, and that ability for water to be in 3 states on the planet, a vapor like in the clouds, or water like in the oceans, and an ice like in the Arctic, or my drink of water. That's the miracle that actually allows life to flourish here. And so I thought that tonight's show should be kind of focused on not just water, but on the basis for all life. And so I thought we're going to talk about that atom that I consider the granddaddy of all atoms in the periodic table, the most important one ever. Okay. And I'm going to ask Amanda which one that is. Do you know, Amanda? Can you guess?
Carbon?
No, first try. Yeah, and she did. She knew it. Well done. I knew that Daryl would know it, and I figured you would know it too, Tara, because we talked about it earlier.
Hey, it says it right up the top of the page.
Okay, spoil sport.
I wish I was clever enough to have picked up on that. I wouldn't have been so insecure with my answer.
See that, Daryl? See that, Daryl? Okay. I actually had a feeling that she probably wasn't going to pay attention to the title because that wasn't something that was important to her right now. She just knew there was a title. It doesn't mean she didn't see it. We pick up things all around us all the time that we don't really register, but that we capture. But you got it right, Amanda, and I'm really proud of you. Okay. So, and when we do this, okay, when we do our Sky Tour radio, we call it a companion show to Sky Tour Livestream. And Sky Tour Livestream is our observatory out in the middle of the Arizona desert. And this is it right here. We have one here in the East Coast too that we're rehabbing and refurbishing, which is what this telescope is behind me. This right here, this telescope right there. That's the telescope. It's over there. That telescope right there is for the stream out the observatory out here, and we're rehabbing it, and the building's getting built. But because of COVID, the cost of wood has gone skyrocketing through the roof. It's starting to come down now. So we're going to be able to build, and I'll go through those build details because we're using something really cool to get the roof off. It's not going to be like this guy, okay, which Tara put a lot of time in along with Marianne Robb. Okay, this is a garage door system, basically a horizontal garage door. It just rolls right off, and it's really, really cool. And if you notice that door, it says STLS, that's Sky Tour Livestream, done by none other than this one down below me here on the left. She's an artist, did a beautiful job making that door. And it's the contest still stands, which is if you can guess how many bottle caps make up that image, because it is made of bottle caps in their natural colors. They haven't been modified in any way. Yes, there are orange bottle caps in there that make up the door. Yes, there's red ones and white ones. The blue ones, I think, are Bud Light, are they not? Man, Tara?
I think that's correct, yes.
Okay, and then the yellow ones, I think, are some type of orange drink or something, maybe. I'm not sure. You tell me.
There's just a mixture of so many things, of sodas and beers. So
yeah.
Mixture.
And before any of you say something silly, no, she didn't drink all those things. She used to work at a place where she could actually gather the old bottle caps because as an artist, she's always thinking. And so that's why she was grabbing these things. I've been to her house. She collects things. And it's not like they're all over the place. She's an extremely organized collector. She knows where everything is. Okay. And it's in a place where you're not going to find a chunk of it over here, a chunk of it over there. It's all here. This is all there. This is all there. Really, really well organized. I mean, and she did that door. How long did it take you to do that door?
Oh, it was several weeks I worked on it.
Several weeks to make that door.
Yeah. Oh, it's a lot of hammering.
Yeah. It's pretty heavy too. And actually it's a thick door as it is, but then she added a layer and crushed the bottle caps. And now that's all that metal now of all the bottle caps sitting on there too, because they're metal caps. And it's really incredible. Okay. So honestly, what I'm getting at is, okay, doing this and being able to bring an observatory to everybody is something that is sort of a group effort. You know, it used to be me. I want an observatory. And then it became me and other people. And then people who funded it through the GoFundMe. And then people like Tara who did the artwork, you know, which is just beautiful, you know, stuff like that. And then when we go live, people like Amanda and Daryl who join us live on the Sky Tour live streams. You know, that this is what it is. You know, so the I in all this went away a long time ago. It's more we now, you know, and there's no doubt about it. And so we're looking to expand. We have the observatory out there that can house more than one instrument. It currently has one, but I'm thinking of a second one in there to kind of do a different task. And I'm thinking either go wider angle or narrower and more magnified. And I think Daryl would opt for the more magnified one instead of the wider.
Maybe I can help you with that, Mark. We should talk about this later.
Yeah, and Daryl's got some ideas. He's got some ideas, you know, and I appreciate all those. And so that said, we are truly, I think, blessed to have some wonderful folks with us here. And I know we only have like a couple minutes left before we have to break, but I did want to make it clear to you that if you wanted to join us and you want to come on board and get involved with the Sky Tour live stream, it's free. It's on YouTube, man. Look up Sky Tour, one word, live stream, one word, on YouTube. And guess what? You'll see my ugly bug, okay, hugging a world, okay. And thank you very much. And that's right. And then you'll see well over 150 streams that have already been put up there that we did all live. And you'll actually get to learn some things if you're not careful, and you'll see some really cool sights. We actually used to have a system that would take pictures, and the pictures we would take would be very much raw. Okay, they would be raw. You wouldn't get to see all the detail of the object we were taking pictures of until they processed it later. You kind of see a rough, kind of fuzzy, okay, that's a nebula. And then when I show them later, it's like, wow, look what was buried in there. Well, guess what? The new system and the new camera and the new system that we're using, actually, I've made it so that we can do two things. One, as soon as the picture is taken, it is shipped out of the observatory and goes all the way up to a cloud and is on a public server where you can go immediately and look at it. Okay, that's the first thing. The second thing is, the pictures as they're being taken are also processed on the fly, not by me. I have a system set up there that actually just processes them on the fly so that you can see what the almost processed one will look like. Because I do process them after, because why not? And they come remarkably close so people can see these amazing vistas. I think it's just something that I think you should join us. Sky through a live stream. But for right now, we're going to take a break. And when we come back, we're going to talk more to Tara and Daryl and Amanda even, because she's got a lot to say too. I know she does. She's not quiet, not all the time. We'll be right back.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
I don't want to talk about it.
I don't want to talk about it.
Families don't have to talk about everything, but they should talk about how to plan for an emergency. Get tips and resources to make your family's emergency plan.
Welcome to the new KGRA digital broadcasting website, thekgradb.com. Here you'll find great new content, including the KGRA Classics, great shows from our archives. You'll be able to see the show times and information so you can see what show is currently on air. The on-air live button. So just go to this section and you'll be able to hear the show live with exceptional sound quality. We also have the Vault section. Make sure to subscribe to get access to great content and special features. We have the make content for our latest news and events, so make sure to sign up and you can be part of our forum. So make sure to check out the new KGRA digital broadcasting website, thekgradb.com. We look forward to seeing you there, and we hope that you enjoy the new website.
Oh, sorry, you caught me admiring my water. Yeah, I love this and Tara has some too. This is the foundation of life on the planet. and most likely other planets. And speaking of the universe in general, we're going to get to carbon shortly, because that's what we're going to talk about, is the ubiquitous carbon atom and what it means to life here. I did want to turn over Sky Tour Radio to our amazing astronomer, that guy down there in the corner, Daryl Mason. And on tonight's deep dive with Daryl, he's going to take us through a few constellations for which we actually will probably have some imagery of from Sky Tour live stream. So sit back and enjoy. And if you got a widescreen TV, now's the time to put it up on the screen. Go for it, Daryl.
Okay. I hope this works. This is working a little different than it used to. Okay, here's full screen. I'm going to start over in the west at sunset at my house tonight. This is what I will see if I go out. I have turned off the atmosphere, so you see the sun is just setting behind that tree. And notice, please, that after the autumnal equinox that happened on September 22nd, the sun is setting a little bit south of west, okay? And we're headed on the way down toward winter. But I've been thinking about Venus a lot lately. Is my pointer showing up okay?
Yes.
Okay, very good. Well, Venus has been getting farther and farther from the sun, and it's getting somewhat easier to see now, but it's gaining very little altitude. And I did a little checking and a little reading up on it, and I'm kind of sorry to say that Venus is not going to get very high for the remainder of this evening apparition, which is going to last to the end of the year, and into January it's going to go behind. It's going to go in front of the sun, though it will not transit. It will not be an eclipse. It will pass between us and the sun. It's called an inferior conjunction, at which time it will move back into the morning sky come January. But I wanted to try to touch on why this is the case. When we see Venus going around the sun, well, when it first appears after sunset, it's clean over on the far side of the sun. And it's bright, but it's not very big. And as night to night, Venus climbs farther out from behind the sun, it will get somewhat higher, but its separation from the sun increases. And the most we ever see that angular separation, that's called greatest eastern elongation when it's in the evening sky. Venus will be a little over 45 degrees away from the sun, okay? So say the sun sets, then you look about halfway up in the west-southwestern sky, and there would be Venus. But that's an east to west thing. Now, why we're not going to see it climb very high this time is because of this red line. This is the ecliptic plane. This is a projection of Earth's orbit around the sun. Actually, the sun's motion in the sky over the course of a year, and the other planets also tend to follow along the ecliptic plane. They may not be exactly on it. You see there's a little space there. Now, this is Mercury, and Mercury also is a little bit south of the ecliptic, and there's Mars about to go behind the sun right now. We're going to lose contact with the Mars probes here shortly for a short amount of time. But this time of year, that angle that the ecliptic makes to the western horizon is a very shallow angle. You may have heard me talk about the analemma before, that figure 8 out in the Pacific Ocean, which shows the course of the sun over the course of a year. And we just crossed the celestial equator, the sun did, heading south. And, well, the angle of the ecliptic this time of year is shallow in the east and the west. Now, this is because during summertime, the sun runs high in the sky. It is up in the high part of the ecliptic in the winter sky, the constellations of the winter sky during summertime. Okay, they're behind the sun and we can't see them, but that's why the sun is high, and that's why summer is summer. You know, we're getting more sunlight than we are dark. But we just went through the autumn equinox, and now the sun is moving farther south day by day, and we're still seeing where the sun being high in the winter constellations is now moving to the sun being high in the summer constellations as we go around the sun over the course of the year. The long story short, though, is we're only going to see Venus get about 22.5 degrees at its highest above the west-southwestern or southwestern horizon. It will, at its greatest, be 45 degrees or so east of the sun, but it will never gain a lot of altitude this time. And this varies apparition to apparition. It's all depending on where we are, what time of year, and where that angle of the ecliptic is when it happens. Now, I'm going to move over to the south, and you can still see the stars of summer are going away now. Here are the constellations. There's Scorpius. The Venus is in Libra. Backing up for just a second, you see Virgo starting to go behind the sun already. But here are the stars of summer, the constellations of summer. Venus is in Libra. Here is Scorpius, already west of the meridian at sunset. Sagittarius is about to cross the meridian. And then all the other bright stars of summer, okay? But note still that when we look at that analemma out in the Pacific Ocean, at its southern limit, that figure 8, the bottom of the figure 8 is only 23.5 degrees below the celestial equator. So for me, my southern horizon is 50 degrees south. Take away 23.5. Well, it's only 26.5 degrees above the southern horizon. Now, this is why Venus is going to stay low this time around. Now, as we progress later into the year, I'm going to change the months here. You see how the plane of the ecliptic is starting to ride high up in the fall and the winter sky, where by the time we get over to the winter stars, okay, I mean, here comes Orion, and the planet, I'm going to have to go a little later in the evening here. By the time we're into winter, okay, the sun will be up, the winter stars during winter time, well, the sun is set at the highest part of the ecliptic at that time. This is when we're at the top of the figure 8 in the analemma. The sun will be in Gemini. Now, it's called the Tropic of Cancer when it's farthest north, and the Tropic of Capricorn when it's farthest south. But because of what's called the precession of the equinoxes, over the course of 26,000 years, you may have heard, the North Pole makes a great circle in the sky of 47 degrees or so, about 47 degrees, and it shifts over time. So from the time when they plotted out all this, when they figured out the signs of the zodiac and, astrology, whatever you want to call all this, well, the sun has moved about this far over into Eastern Gemini, almost going into Taurus, actually. So we could say nowadays that instead of the Tropic of Cancer, it's the Tropic of Gemini. But when we see, I'm going to go back to present time. Okay. And pardon me while I flip around here. Okay, a little after sunset. Saturn and Jupiter will still, of course, they're also on the ecliptic, and they're running low in the summer sky now in Capricorn. But when a few years from now, let's go forward a few months. Again, let's see. Bear with me here. Okay. You'll see in January, Venus will have gone by the sun and is in the morning sky. It will in the winter time. You see that angle of the ecliptic is much steeper, and by springtime, I'm going to go forward a couple more months here. Okay. When we see the plane of the ecliptic in the spring, okay, you see how steep that angle is. At that time, it's much steeper because we're looking at the part of the ecliptic that is climbing up high into the winter constellations. I hope that all makes sense. Anyway, that's why Venus isn't going to appear very high this apparition, I'm sorry to say. But now, okay, we're getting back to now, and here's tonight, about an hour after sunset, and we're seeing all our old friends now. Scorpius is declining in the southwest, and here comes the Sagittarius teapot. And as we go up the Milky Way, well, Sagittarius, Scutum, the shield, there's Ophiuchus, the serpent bearer, there's the serpent's tail, there is a serpent's head, and on up through Aquila. The summer triangle is going to pop out here. Okay, there's Vega, there's Altair, and this little friend Terazed right there. And Deneb, there is a summer triangle. It's going to start going away. By later in the evening, let's call it 10 o'clock, 10:42, you see Vega is already well west of the meridian and is in decline. Cygnus is transiting the meridian. But still following the Milky Way up, well, there's Aquila, there is Sagitta, the arrow, there is Vulpecula, the little fox, and there is Cygnus, the swan, and the Northern Cross right there. That star is Deneb, the tail of the swan. There is Saturn. There is Alberio, that pretty double star that Mark shows us all the time. And we have kind of been moving up this way for a while, trying to get her to go here. Okay. And Mark has been trolling this area in the sky here from near the head of Cygnus. If you have seen some of his latest images of the North American Nebula, which is that right there, and what it says is C20. Okay, that's North America, and the Pelican is right next to it. And then climbing, whoops, okay.
Yeah, there you go.
Yeah, let me get the meridian back here. Okay, going on up. Well, we see Cassiopeia. Boy, I'm having a hard time here tonight.
It flips over, by the way. It's kind of weird the way it does that, Daryl.
Yeah, that's why I try to keep the meridian straight up and down. But then from Deneb and the North American Nebula, well, there's a little constellation called Lacerta, which means the lizard. And then there's Cepheus, that house shape. That is the king. And here's Cassiopeia, the queen. And here's Andromeda, and there's the Andromeda Galaxy. And then here's Perseus, the hero, coming to the rescue. Andromeda's riding on the horse, winged horse, Pegasus. And lately, this is the part of the sky that Mark has been trolling in. And I think I'm going to hand it over to you right now, Mark, so you can go to see some of the neat things that we have been looking at recently.
Well, sure. I mean, if you could just point out Alberio again, I think I'd like to show Alberio, because I actually had Alberio for everybody to show them.
Very good.
I'm gonna probably make you zoom in to all these different things.
Well, there's Alberio right there. And when you see the summer triangle, if you draw the triangle from Aquila to Vega to Deneb and back, and you draw a line from Vega to Aquila, if you look a little less than halfway from Vega to Aquila and a little bit to the left, you will see Alberio there. And
Yeah,
we're gonna zoom in. And here is Alberio right there.
Doesn't look like much there, but in reality, let me show you what it really looks like in a telescope.
Okay, I'm gonna hand it over to you.
Oh well, you stick around because I'll have you navigate into a few things. It's okay.
Okay,
this is Alberio.
Thank you.
Yeah, this is Alberio. It's a beautiful K star, which is orange, and a blue star, which is a B-type star. And these stars are actually orbiting each other, but guess how far they are from each other? They're over 5,000 astronomical units. That's 5,000 times the distance of the Earth to Sun. Keep in mind, okay, the outer solar system is only at around 30 astronomical units. Okay, so you've got to go, thousands of times more than that to get to the 5,000 astronomical units that Alberio is orbiting. This, Alberio A is orbiting with Alberio's B component. So it's actually really interesting how that works. So people have asked me, can there be planets in between there? Well, the answer is not likely, but only because the evolution of this star, this K star, was a different type of brightness a long, long time ago. It was actually a star that was smaller, one that was fusing hydrogen into helium the normal way that stars do. But then it changed. It ran out of hydrogen and it swelled into a large star. Well, any planets that are in between those two stars would likely be planets that could not support life anyway. So could there be planets? Yeah, maybe. We don't know of many stars that are B-type stars that have a lot of planets, but we do know of K-type stars that have planets. Okay, I'll give you one example. Tabby star. Remember Tabby star, the star that seemed to be dimming for the last 100 years? And they had thoughts about it. Maybe it was actually a Dyson sphere, a completely encapsulated star that was being built by an advanced civilization to harness all the energy of their star. Well, it's a K-type star. So really interesting stuff there. But that's Alberio, and that's the head of the Swan, in Cygnus the Swan. So you have the constellation art right there. You can just pop that up to show folks.
I do.
There you go. So there's the head of the Swan.
There's a great big old swan head right there.
Right. Now, if we want to follow that back towards Satur, which is the center Gamma Cygni, it's called, which is it's the third brightest star in Cygnus. That's they use the Greek letters, right? And Satur in the center. This is an area of the Milky Way, okay, where we're looking at a spiral arm of the galaxy. We're looking dead into, I should say, one of the spiral arms of the galaxy. And when we look at it with our eyes, we see a faint cloudiness. But with a telescope, ever so slight of a telescope, we actually see things like this. This is the nebula, for instance, that's around that star. You'll see Saturn, that SADR star. You'll see that here in this view. It's there to the right. But this here that you're seeing on the screen, this is a cloud of hydrogen gas. It's hydrogen because it's glowing red. It's not being illuminated by a red star. It's glowing red on its own, and that comes from what's known as an atomic transition through something called ionization. Hydrogen gas is a proton and an electron, and when the electron is hit with a lot of ultraviolet radiation, like from stars like Saturn, then the electron can go higher and higher and higher in its what we call a cloud around that proton. That's the singular proton that's in a hydrogen atom. And eventually it could actually get loose. And when it leaves the atom, for however short a time, that's called ionization. And it doesn't take long for that electron to find a home, whether that same atom or another atom that's lost its electron of hydrogen, and it will drop into the atom. Well, they drop into many different levels, but they drop into one level predominantly, and that's a level called n equals 2. Don't worry about that. It just means that it drops to a certain space, a certain quantum location in the atom, a certain specific delineated location, and that gives off red light when it does that. Okay, there's other places it drops into which don't give off red light, But the predominant reaction that you see is this one transitioning to a red light. That's why nebulae tend to glow red, right? And that's the nebula that's called the Gamma Cygni Nebula. And of course, Sadr is Gamma Cygni, the third brightest star in Cygnus. And we go alpha, beta, gamma, delta, all the way to omega. All right. So now Daryl mentioned the North American Nebula before. So he's pointing to it right now. Yep, you got it. And now when you look at that, you say, well, with your eye in a dark sky, it looks like a faint patch, but brighter than the rest of the area around it. But with a telescope, then you can get the full detail. This is the North American Nebula. By the way, this is a 20-second exposure. That's 20 seconds out at SkyTour Livestream West. Okay, now you can see the feature that looks like North America to the left. Okay, that little area coming down around the lower left there, that looks like Mexico. Then that black area in the center, that looks like the Gulf of Mexico, and then Florida to the right of that. So that's why it's called the North America Nebula. Not the North American Nebula, North America Nebula. To the right of it, you see a nebula that looks vaguely reminiscent of a pelican, and it's thus called the Pelican Nebula. And the back of the pelican's head could be that little darker red knobby area to the upper right of that right side nebula. The dark eye could be, that dark eye you could see there to the lower left of that with a little tiny star above it. That could be the eye, and then the beak, of course, goes further down to the lower left. That's one of the interpretations. But
that's a great picture.
And isn't it beautiful? And for 20 seconds, I don't know. You can't beat it, And by the way, this is almost exactly the picture that people saw during the stream, because we actually do this on the fly processing. So you saw this, almost nearly this, when we actually took the picture. So you get to see this stuff, and it's just cool.
Mark, can I say that
Yes.
just for someone who is not on Facebook or other things, it's so great that we can see these pictures live now, because I never really got to see the processed photos. So thank you.
No, that's great. I'm glad. And remember, we also have the live server that as the pictures are being taken, they're shipped out of the desert off to a server, wherever the server is, okay, wherever it is in the world, it's shipped there. And then anyone can access it. And the address to that server is given on my Facebook page for Mark D'Antonio, or on the SkyTour Livestream Facebook page. They're pinned posts at the top. And they're there. And you can see where the server is. Go there. And you can even see the test photos I took just the other night. Even if I didn't publicize it, they're there and you can see them. And I name everything so you see what they are and all that. And I also provide the raw stacks. Now, what are those? Well, take a picture like this one or like this one. They're 20-second shots, yes, but it's a bunch of 20-second shots that are aligned and stacked with each other. So when we talk about stacking these things, okay, what it really means is that we're trying to figure out a way in which we can, I'm going to try and just do this for a second. Okay, what we do is we actually align the pictures with each other. So we line them right up, or not so they're not off center anyway, but lined right up. And that's done automatically. And then once they're aligned, the data from, say, this picture is added to this picture. And if you stack a bunch of them, then you get more data than you do noise. Because noise is also relevant to this whole equation, and it's there too. We'll see noise in these images. The first shot is always noisy. You see all this grain and color blotching. But as it keeps going and stacks more and more and more and more, it's live right before your eyes. You watch it come in clearer and more beautiful and more beautiful. And you know something? And I do have to thank Tara, because Tara actually was one of the people that went out to the observatory because we've had issues out there, and she's driven all the way out into the desert to make adjustments and repairs and help us fix things. So that person down there, doesn't give herself enough credit. So, I do. So that's
pleasure.
What's that?
Give her a raise.
Yeah, you know what? When we start getting paid for this, I will. So that said, that is that's that. Okay, Daryl.
Whoopsie. Hello.
That's okay. Go ahead. You can full screen it. So another thing in this region here, okay? Did you do that again?
Hmm?
Let me do this. There we go. Okay. So we talked about the North America and the Pelican Nebula. And now also in this region is something else. And I'm now talking about the veil.
Right
so you might
there.
know where the veil is.
Yeah, that big oval right there.
Yeah. I mean, it looks like an oval, but you know what? There's more to it than that. Because if you were to actually take a photograph of the entire thing that's within that oval and show what it looks like, well, here it is. It looks like this. This is the whole object. At the upper left, you see that gossamer arc of material that looks like it's multicolored. To the right of center, you see this haphazard-looking collection of material that looks like it's multicolored. And then to the lower right, you see a much more sharply defined object that is also multicolored. And what that is the Veil supernova remnant. Now, at the point in the past, there was a star right where that central, right in the middle of that ellipse that Daryl has highlighted right now. Okay. And that star went supernova at one point. And when it did what stars do. They return the elements to the interstellar medium. It's really, really incredible. And again, I know we're coming up on another break, but we'll take that in a second. I just want to share with you that when we come back, we're going to talk about more of the Veil supernova remnant, okay? Because there's the whole thing, but that part on the upper left, well, that's here. That's this. And another version of it, even closer, is here. You look at all the detail. There's a lot of detail here, folks. But you know what? In spite of the details that we have now, I'm going to turn it over to a commercial break. And when we come back, we'll talk about more of this and get to some really interesting questions from our own Tara. We'll be right back.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
I don't want to talk about it.
I don't want to talk about it.
Families don't have to talk about everything, but they should talk about how to plan for an emergency. Get tips and resources to make your family's emergency plan.
Welcome to the new KGRA digital broadcasting website, thekgradb.com. Here you'll find great new content, including the KGRA Classics, great shows from our archives. You'll be able to see the show times and information so you can see what show is currently on air. The on-air live button. So just go to this section and you'll be able to hear the show live with exceptional sound quality. We also have the Vault section. Make sure to subscribe to get access to great content and special features. We have the make content for our latest news and events, so make sure to sign up and you can be part of our forum. So make sure to check out the new KGRA digital broadcasting website, thekgradb.com. We look forward to seeing you there, and we hope that you enjoy the new website.
Hey, welcome back to Sky Tour Radio. This is Mark D'Antonio with Tara, the amazing Cosmos lady, and Amanda Curran, our wonderful co-host, along with Daryl Mason. And we're actually in the middle of Daryl's deep dive and showing some objects that are here in Cygnus. But Daryl, there's one other one that I'd like you to find, which is actually just a little bit back from Saturn. That's the Crescent Nebula. You know where that is? It's right. Yeah, it's sort of in that area.
Is that it?
Well, yeah, it is.
Yep, that's it.
Yeah, that's a good guess.
I'll zoom in there.
Nebula, yeah, that's good. You know, the Crescent Nebula points out something really interesting. Okay, this is what it looks like in the planetarium program that you see here, but here's what it looks like in actuality when we take a photograph of it. Okay, the crescent is dead center. And of course, it's called a crescent because it looks just like a little backwards C, right? Well, it's interesting how these things form. The star in the middle there, the brighter star that you see there, that's actually the star that is responsible for causing the crescent. That's actually called a WR star, or Wolf-Rayet, R-A-Y-E-T, Wolf-Rayet. And these stars can be very, very hot, anywhere from 25,000 degrees to literally over 350,000 degrees Fahrenheit. Okay, so that's like 20,000 Celsius to, 200,000 plus Celsius. And what happens is the stars are regular stars like we have, see in the universe that are fusing hydrogen to helium, but they're massive. And sometimes what will happen is the star is so massive that at some point it starts to literally push its hydrogen envelope away from itself. Once it stops fusing the hydrogen, then the hydrogen is now just essentially inert in the envelope of the star, and it gets shoved away from the star. And that leaves the star kind of open so we can actually see what's going on further deep inside. And we actually see that the star is taking helium, turning into carbon, carbon into nitrogen, into oxygen, and other elements further down. And the end result of the stars that are this massive are that they are going to go supernova someday. So whereas this here looks like a supernova, it's not. It's actually just part of the evolution of these massive stars. And another famous location that we're going to see here in the coming months in Sky Tour live stream is something that Daryl's got on the tip of his tongue. I know he does, so I'll let him say it. Go ahead.
Thor's helmet.
You got it. That's right. Thor's helmet is another object in the night sky that we're going to be able to see. That's another one of these objects, but it's actually far more spectacular than this one. It has got multifaceted tendrils of gas. It's sort of got a greenish red hue. It's just stunning in color. And one of our longtime friends to Sky Tour live stream, Isabella from Bulgaria, she loves to take these images, and she likes to process them. And she'll take all of our raw images and she'll process them for herself. She does a really fantastic job. And we those of us that process love to process, and she loves to process. Well, she got a hold of professionally done Thor's helmet photos that were taken at another observatory, because we haven't been able to see Thor's helmet yet with Sky Tour West, because it's only come online in the last few months. And she processed the Thor's helmet from there. And there's a lot of hidden detail in Thor's helmet that I am really itching to see and pull out. It's going to be beautiful.
Thor's helmet is what? Canis Major, Carina, down in that area?
Thor's helmet is down, is it Monoceros?
I thought it was farther south.
It could be.
Anyway, it's a winter constellation, so you'll just have to wait, folks.
Yeah, I know. Amanda, you were going to say something?
Yeah, speaking of processing, someone in chat asked earlier, how many images on average do you use to stack? Like, do you stack for full picture?
Well, you know what? It varies, but I'll tell you on average, our exposures are about 20 seconds long, and I'll capture perhaps 30 of those. So, if you think about it, that's only 600 seconds. And in that time, we're talking about the object. So before you know it, 30 frames have come and gone. And that's getting shipped up, and people get to see the process shot. It gets clearer and clearer, as I mentioned, and it's really, really pretty. I was going to stream tonight, actually, after the show out there, but I don't think that the weather's conducive out there, and we have to be careful. You know, it is a remote observatory. I'm operating it from Connecticut right now, and it's out in the Arizona desert. So if something goes wrong, I can't just reach out and fix it. You know, I could ask Tara, please go visit. And Marianne Robb left a comment earlier that you saw. Marianne is the other moving force in Sky Tour live stream as well. And, she's another one that will go out there and tend to things when I can't be there. And they do a phenomenal job. So I think that if you think about it, 600 seconds goes quickly, and the stacked image is automatically stacked, automatically processed, and automatically aligned to get all the miss movements out of the way. And we can even do other processing to help sharpen the image dynamically along the way, along the fly. And it really comes out so nice. So that's about 30, I would say. I've done less. And it depends on the object. If the object is bright, we don't need to have 30. When it's faint, okay, then it might require that many more. Okay, this one I believe was 36 images, maybe 40. And I don't remember if we were actually live streaming this or if this was actually a private stream. I do private ones when I want to just do some research shots and stuff like that. But anyway, so there is that. And Daryl, I don't know if you have any more. If you'd like to do more, please feel free.
I don't want to dominate the show.
You're doing
I know
fine.
you've been working. Darn it, I'm trying to get around here. I'm upside down. There we go.
I did do the elephant's trunk, if that's where you're going.
Yeah. Let me get a setup here. Elephant's trunk, refresh my memory. Where exactly are we? Cassiopeia?
Yeah, it's down. It's going to be down in Cassiopeia, down that region.
Okay, here's Cassiopeia.
Start zooming, you should see it. It's off, I think, over to your left. This image. Yeah, I don't. If you're not seeing it now, I could just show it, and it might be down further actually, more toward the pole, because the Wizard Nebula is down in that region too. Yeah, see, you got the double cluster, so it's actually. Let's see. I think you're talking. It's got to be. No, not down there. I don't know. What's that right up the top there?
See, I think this is incredible that you guys can actually read a map of the sky, of the universe, of the stars and constellations like you're searching for a house in a neighborhood.
Right?
That's incredible to me. So just take in, appreciate what's really going on here, folks. They're that detailed. Oh, it's just past the double cluster, just a little low of Cassiopeia. Like that's one day.
Well, give me a second here. I'll cheat.
You could. What's the left of center there, though?
I think you have to take a left at Albuquerque.
I think you're right.
Turn left at Greenland.
Daryl, is that nebula right there, just below center? What's that?
That?
Yeah. The flaming star? Oh, it's just a high proper motion. Wait a minute, that's a high proper motion star. Is that okay? That's not Barnard's star.
Hard to believe we lost a whole elephant in space.
Oh, I actually have pictures of the elephant. You won't miss it. It's beautiful.
Well, go ahead and show your picture, Mark.
All right, you keep looking. But anyway, down around Cassiopeia, there's this area that has a lot of what we call dark nebulae. And here it is. Okay, this is the Elephant's Trunk Nebula. Now, what's the Elephant's Trunk? Well, it's that part to the right that's sticking in from the right side, and it seems like it has a hole in the middle of it at the end. Looks like a needle with an eye at the needle. You find it?
Elephant's Trunk is in Cepheus, yeah.
Okay, Cepheus. Okay, yeah. All right. Hey, we were close.
Hey.
Yeah, so the Elephant's Trunk here, I want you to notice all this dark nebula that's in here. There's this dark stuff. Now, those aren't voids. Those aren't areas where the stars are gone or missing. There's areas where they're obscured by dark material. And what is that dark material? That dark material is dark dust, not gas. You can see through gas. This is dark dust. And that dark dust is, by and large, made of carbon, more of that ubiquitous element we've been talking about before. And there's some data about carbon that makes it really, really important. And we're going to talk about some of that as well.
Yeah, nice segue.
Well, yeah, no, but still.
Oh, yeah.
But the thing is, besides the carbon that we see in the dark nebulae, okay, we have lots of carbon here on the planet, okay? We also have carbon in other processes that happen throughout the universe. And I know Tara has been putting together some really interesting questions about carbon. And if you'd like, Tara, we can just segue over to you to talk about some of your questions about carbon, if you like. Because I also have more to say about carbon after that, but I would like to give you a chance to ask some of your questions because you just sit there waiting so patiently.
I'm learning so much all the time, so I have the patience. It's very cool. Well, you're talking about the carbon cycle to some degree, and one thing that I'm not really clear on, one of those cycles is respiration. And so can you explain what respiration is and how does that affect the carbon cycle and why should we care, if at all?
That's really interesting, Kate. On the planet, people know, well, there's a water cycle, right? Water's in the ocean, it evaporates, goes into clouds, it rains, it goes down to the ground, trickles back into the ocean, and the cycle starts all over again. Same thing happens for other elements on the planet too, other molecules, other compounds. And one of those is the carbon atom. It happens with carbon as well. Now, let's first define what the carbon cycle is, okay? The carbon cycle is a methodology, a process by which carbon can leave the ocean or leave the earth, go into the air, make its way from the air to the ground, back into the sea and back into the air, into the seafloor and things like that. But what does that really mean? And there's a variety of ways that the carbon cycle actually occurs. And I would actually like to show you something that might indicate that. That's not it. But this is it right here. There we go. This is the carbon cycle. And this is something that's really interesting because I'm trying to get this. Oh, I can't do it this way. Okay, never mind. All right. So if you look in this image here, you'll see at the top it says CO2. That's carbon dioxide. The Di means two, and dioxide, 2 oxygen atoms. So the carbon dioxide. And you'll notice that on the left, the green arrows show you how carbon is moving. Okay. And when you see in the upper left there, you see the green arrow pointing from the CO2 in the atmosphere down to photosynthesis. It means that during the day, plants are going to take in this CO2, and the CO2 is used to make glucose. And how do they do that? Well, that's a little more than that we have time for the show, but the glucose, the chemical formula is C6H12O6, and that's 6 carbons, 12 hydrogens, and 6 oxygens. This is the fuel that fuels the fires of photosynthesis and plant life on the planet. They make glucose, and this glucose is then used by the plants, usually at night. Okay. Now, what happens is during the day, when a plant is pulling in carbon dioxide, all right, at the same time while it's making this glucose for its fuel, okay, it is taking this glucose and it's utilizing some of it to continue its metabolic processes, okay? But at the same time, the plant is also, in order to stay warm, it basically perspires, but it's called transpiration. And so what happens is, as the plant perspires, it's giving off water off its leaves, and the leaves, that water evaporates into the air, and it keeps the plants cool. And that's called transpiration. But you're asking about respiration. Well, that's the other side of the coin. And on the other side of the coin, that happens at night. At night, what happens is the plants are going to use this glucose, because plants actually grow the most at night. I don't know if you knew that, but they actually grow and develop the most at nighttime. And so they will actually then release some CO2 at night. And that's the process called respiration. And so that is part of why it's included in talk about the carbon cycle, because the carbon and the carbon dioxide is being released to the atmosphere at night. And it's also being taken out of the atmosphere during the day, during the very energetic process of transpiration, where the plants are making oxygen, basically. And we've talked about this before. Plankton, phytoplankton, make up about roughly 80 something percent of the oxygen generators on the planet. And the rest of the forest do the rest during their transpiration cycle. All right. And then during respiration, of course, as I said, the carbon dioxide, some of it's released, and the plants grow during the nighttime hours.
Can I ask a question?
Yeah, go ahead.
Is glucose like Brondo? It's got what plants crave?
It's got electrolytes.
There you go.
That's pretty good. That's pretty good.
Sorry, I couldn't help myself.
You know what? That's okay. Sometimes, sometimes it's appreciated. And now is not one of those times. No, yes, of course it is. Now is one of those times as well.
I'll go sit in the corner.
No, you won't. You're okay.
I have a question, Mark. You're talking about plant respiration, but I see in your chart here there's animal respiration. Is that like our breathing?
Yes.
Okay.
It is. That's a little confusing, because when you think of respiration, you think of plants as taking one breath per day. Okay. So they're going during the day, they're inhaling. Okay. And then exhaling at night, right? That's kind of like the mental picture. And when we exhale, we give off carbon dioxide. Well, they also give off carbon dioxide at night. When they inhale, they're actually taking in carbon dioxide, and what they're actually generating as a waste product effectively is oxygen. And I think that's kind of interesting. So, but their respiration, the only way it involves oxygen is that for a plant, carbon dioxide is their oxygen fuel, basically. See what I mean? It's the fuel for the plants. It's what gives them the fuel, along with, of course, the sunlight, which is generating the photosynthetic reactions. I remember studying photosynthesis in classes about the makeup of spaceship Earth, basically, and it's a really, really complex process. There's nothing simple about it.
That's a really pretty analogy. I've never heard it explained like that before.
Yeah, I mean, that's sort of how I think about it.
Yeah,
I think that's how people should think about it. Think about plants taking one breath per day.
Yeah.
We take one breath every 30, 20 seconds, maybe 10 seconds. And the plants take one breath a day. A singular plant, in a sense. So that's something that we obviously depend on in a carbon-based life, in a carbon-based program that we are. And we are a carbon-based programmed object, aren't we? So does that help answer your question there, Tara?
Yes, it does. It's basically, you're saying so that, let's just confirm, all living things contain carbon, correct? And so do all living things contain like the oxygen and hydrogen and nitrogen, the most basic elements there?
That's right. And in fact, life on Earth. What's that?
Chomp.
Yeah, chomp. I was getting there. You're right. That's right. The chomp is exactly what we talked about: carbon, hydrogen, oxygen, nitrogen, and phosphorus. Okay, and sulfur, by the way. So it's chomps. Okay, and the sulfur is actually in your bones. Believe it or not, there's a lot of sulfur content in your body that you don't even realize is there. But that's also effectively the building blocks, I would say, for things like DNA. And the carbon atom is at the core of it all. The carbon atom, if you look at the carbon atom, all right, it's number 6 in the periodic table, and it has 2 electrons that are near the center and then 4 on the outside shell that it can bond with 4 different things at once. Okay. That's something that makes carbon very valuable. And I've heard it talked about before, Tara, that, isn't it possible that silicon can be a good, basis for life like carbon is? And I know that in shows like Star Trek, you see a silicon creature that, pits Captain Kirk against the others to have a combat or whatever. Well, silicon-based life is just not feasible. And there's a bunch of reasons. I actually can tell you many of the reasons, but and I will because I don't know when to shut up. But you can shut me up. But the truth is, if we look at carbon, it's literally the 4th most abundant element in the universe. Okay, 4th. Right? We have hydrogen, we have helium, right? Right. We have carbon, and one of the things that's interesting about this is that when we follow how the carbon is developed by stars, we can see why it's very abundant. Because stars make it in their later lives. Supernovae expel it in their later lives. And so it's effectively like soot, S-O-O-T, soot from a fire. And from a chemical fire, the soot is carbon. Okay, so I know that, carbon is everywhere we look as well. So it stands to reason that if that carbon atom was very flexible, it would stand to reason that carbon might end up becoming the basis for life on the planet. Okay, but let's take a look. For instance, I know that I'm just saying carbon, and I know everybody thinks, well, what about other elements? Let's talk about some of the other elements. Okay, and to do that, we want to talk about the periodic table just a little bit. It's a scary thing, and everybody hates this thing. What is that? Get it off.
Run away.
No, run away. Okay, but if you look, okay, just to the right, underneath where it says the periodic table of elements, well, underneath the second E in elements, you can see carbon at number 6 right there. Okay, and then just below it, you see silicon, right? Now, everything in the column on a periodic table, so you have carbon, you have silicon, you have germanium, you have tin, and you have all the rest down there, lead and so forth. When you look at those going down the list there, they all share similar properties. That's why they're in the same column. So people say, well, if carbon can be the basis of life, well, then maybe silicon, which is very, very similar, can be the basis of life. And the reason that we don't look at something down here like bismuth and say, well, maybe bismuth or lead can be the basis of life. The reason we don't do things like that is because these elements, as we move further down the table, are far less abundant. And they're just not there in the sufficient numbers to actually make life in any way. So that's part of the problem we have. Okay. So let's just take a look here. Let's start with hydrogen. Okay. Hydrogen up in the upper left, number 1 in the periodic table. See it? There it is. Okay. It's the most abundant element in the universe. It has 1 proton, it has 1 electron. And hydrogen is something that can only bond with one other thing. Okay. Can only bond with one other thing. And that's because it has 1 electron. And the number of electrons will, determine how many things something can bond with. So it's not even remotely flexible enough to support complex compounds and bonding that's required to make a life form. So we move on to number 2, all the way across the right side of the table, helium. Now, helium is strange. It has 2 protons and has 2 electrons. Ooh, so you think, oh, that's two electrons. Maybe it can bond with more than one thing or 2 things. Well, the answer is it can't. It's a real snob. It doesn't bond with anything. And you might say, well, then how do we find it? Well, believe it or not, in radioactive decay underground, helium is released, and it ends up being in pockets of rock as helium gas, and it's extracted that way. So in a sense, we can say for sure that we're always running out of helium on the planet. There will be a day when you'll never be able to talk like this with your voice because there's no helium anymore to do it. You know, I was going to do that for real because I do have a helium tank back here, but I figured I better not do it because you could pass out, and that's very embarrassing on live radio, on TV. So we can't really consider helium then as a foundation for complex life. But then you look, down after helium, you go over to the left and then the next row, and you see number 3 and 4, lithium and beryllium, and then 5, boron. And you say, oh, what about those guys? Maybe, except for the fact that lithium, beryllium, and boron don't even have remotely the numbers that we need. Only a small amount was ever made in the very beginning of the universe. So there was never enough to even support any kind of life, never mind create complex interactions. So they're out. So next we have carbon. All right. But I don't want to skip that for now. We're going to come back to carbon. Let's look at nitrogen, the next one over, number 7 in the periodic table. Nitrogen is abundant on the surface. It's abundant in our air. It's 80% of our atmosphere, and it's diatomic, meaning it's nitrogen two nitrogen atoms put together. Okay. And so it's really, really out there. And it also bonds with a number of elements like hydrogen and oxygen and carbon. And proteins are very long molecules, and they're formed as long molecules made of amino acids with nitrogen in them. Nitrogen is fundamental. And DNA, well, it's got DNA as well that has nitrogen in it. So how come nitrogen can't work as a basis of life? Well, it turns out nitrogen actually forms bonds with these other elements that are too strong. And this means that it can't show the flexibility that's required for the basis of life. There's a lot of breaking of bonds and reassembling of compounds that occurs when life is made and when life is in operation. And nitrogen can't do that. So let's move on. What's next? Number 8, oxygen in the periodic table. We're not going to go through the whole periodic table, I promise. Okay, we're almost done. So why not oxygen? It's the most abundant element in the Earth's entire composition, right? There's more of it than anywhere else, okay? It's found in all the rocks and all the minerals. And how about this? Here's a little analogy for you. When you stand on a beach, you're standing on what? Sand, right? And sand is actually got a chemical formula of silicon, and then 2 oxygens is bound to the silicon atom. So it's silicon dioxide. That's sand. So isn't it interesting to know that 2/3 of your support when you're standing on a beach is done by oxygen atoms, and just one element, one silicon atom. But 2/3 of everything you're standing on is actually provided by an oxygen atom. Oxygen is a gas.
That's weird.
Isn't that weird?
That's really weird. Even Dingo thinks so.
Even Dingo, well, she's actually trying to get in here, and she wants to talk about silicon as a possibility, but that's not going to work. Okay, so and the thing is, oxygen outnumbers carbon by 1,000 to 1, and you think, wow, there's so much of it. Why wouldn't that be capable of providing a basis for life? It bonds with almost everything, and there's no specializations across the board. It'll bond with anything it wants at any time for whatever reason. In other words, biological constructions that we see in life, okay, they utilize ring structures of molecules, rings of molecules, long chains of other molecules. Guess what, though? Oxygen alone cannot support these arrangements. So it's not a good building block for the foundation of life. It can be utilized by life for energy, like plants use it to build glucose, right? But it's not something that actually can provide us with a good building block foundation. So moving on a bit, the inert gases that we talked about, one of them was helium. And then down that vertical column there, you see on the far right, helium, neon, argon, krypton, xenon, radon, and aganesian. Okay, don't worry about that. But those far right ones are called noble gases, and they really don't bond with anything. So they can't support life's arrangements. So guess what? They're right out of the picture right off the bat. And that brings us to that other one that people talk about in science fiction all throughout, and that is silicon, number 14 in the table. It's just below carbon at number 6 there. And silicon is one that people say, hey, silicon can create, you should be able to be a basis for life. I've seen it in Star Trek. Well,
No Kill Eye.
No Kill Eye, and also the rock monster. Remember the rock creature on the volcano planet?
The Horta.
No, that was the Horta. That was the driller. Yeah, but there was also this rock creature that sounded like rocks rubbing together every time it moved. And I know
right.
Remember
Okay.
that?
Had a real bad attitude.
Yeah, it had a bad attitude and wanted to see them kill each other. But as it showed, as that episode showed, carbon-based life thinks much better than silicon-based life. Well, so you might think that silicon might be a good possibility. Because if you look below carbon, as I mentioned, in the columns in the periodic table, these elements all have similar properties to each other. But they're in lesser and lesser abundances as you go down. So the next one down from carbon is silicon, and that might be a contender, right? So what we do is we look at the possibilities and we say, could it be the basis of life? And the answer is not really. And the reason is because, and not as much as we would like, because consider the early Earth. Silicon was in abundance, and oxygen was in abundance after a certain period of time. Okay, as soon as the photosynthesis started taking place. And the silicon and the oxygen bonded tenaciously to form those silicon dioxide, as we talked about. But guess what? The bonds between those two atoms are so powerful that it makes variations of those next to nil. You can't get any variations, really. And so it meant that silicon is not even remotely possible as a basis of life. So much for sci-fi, huh, Tara? Yeah, she's got to mute.
I was muted. Sorry. So much for that.
Yeah. But if we keep going down the periodic table that we have here on the screen, you go to number 26, kind of in the center of the blue, light blue, iron. Okay. Iron is interesting. Maybe iron can do that. Iron does bind with many and bond with many different types of atoms, including itself. So that's a good thing. So why can't iron be the basis for life? When iron bonds with another element, it forms many different compounds, many thousands of compounds. So would that not be something that would be good for us to use to think of iron as a possibility? And the answer is, hey, maybe it would. Maybe it would. But what about iron makes it unsuitable? Well, the iron has a property, and unfortunately, it is that when iron binds with any other atoms and to form another mineral, it tends to make a very large crystal mineral. Okay, if you think about what that means, and I don't mean crystals as in clear crystals, like when you look at a quartz crystal. Ooh, quartz crystal. Ooh. No, but how about something along the lines of this? This is Devil's Tower in Hewlett, Wyoming. Now, I had the fortunate opportunity to speak there twice at a conference, and I spent a lot of time looking at Devil's Tower. And Devil's Tower is not made of basalt lava. Basalt is one particular chemical composition. This is actually made of phonolite. Phonolite porphyry, it's called. Phonolite porphyry. And phonolite porphyry is got iron atoms in it. But the atoms of the iron make large crystals, which actually give the appearance of this large lava thing sticking up here to be like it's got like a tree bark on it. Because if you look at it up close, this is what it looks like up close. Do you see the size of those crystals? You can tell how big they are because just above and to the right of center, that's a person standing on top of one of the crystals. They're about 8 to 10 feet across. You see that? And I took these pictures at Devil's Tower. And you can see another guy just below
There's
center.
2 people, yes.
Right. And we watched them climbing and went all the way to the top. Now, but you can see the size of these crystals. Well, unfortunately, iron tends to make only these large crystals when it bonds with another compound, another element, make a compound. So it makes it unsuitable to support life of that varied molecular type that we need. Small molecules just don't exist in the iron world, so to speak. So it would be very much impossible to create this type of life in iron. So this gives you an idea of why carbon is the most effective. And carbon can bond with hundreds of thousands of additional elements and make new compounds. I should say it makes hundreds of thousands of different types of compounds with ease. And the bonds, some of them are tenacious, some of them are weak, some of them are acidic, some of them are not. It has many different types of groups and functions and capabilities. And it's the carbons, the basis of the carbon is what's giving it all the teeth that carbon has. So that's why carbon is so important to us on the planet. And if we want to look at just, for instance, at just the abundances, let's say we have 1 million atoms. So let's say we take a net and we capture 1 million atoms out in the interstellar medium. Okay, of those, 739,000 would be hydrogen. That's like a lot. That's almost. It seems like almost all of them, right? Well, 240,000 would be helium. Okay, 10,400 would be oxygen, the next most abundant. And then carbon with 4,600. Okay. And then from there on down, it goes down to just like neon is 1,300, iron 1,090, nitrogen, believe it or not, nitrogen being so prevalent in our crust and in our atmosphere, you think it might be really abundant in the universe. It's not. It's the sixth most abundant. It's actually 960 out of 1 million atoms would be in nitrogen. Then there's silicon at 650. So there's not a lot of silicon. Keep in mind, carbon had 4,600. Silicon had 650 out of 1 million. Magnesium 580 and sulfur 440. So you can see, and all the rest are trace elements, by the way, far less than that. So you can see that this is the abundance level. Hydrogen's the most, helium next, oxygen next, and then carbon. So it stands to reason that if there's going to be a basis of life on any particular thing, that it was going to be carbon. Because we know oxygen can't do it. We know helium and hydrogen can't do it. So carbon is the next contender. And you'll notice that silicon isn't even on the list until after neon, iron, and nitrogen in terms of abundance. So we're talking about a universal abundance that makes carbon the most likely contender. So when people say, well, there might be life out there based on another type of element, not in our chemical world, not in our understanding of the periodic table, not with our understanding of chemistry. I think that life out there will most likely be carbon. And I've said on this very show before, yes, I am prejudiced. Yep, I'm a carbon bigot. That's right. You got a problem with that? And again, it's because we're carbon. Now, one of the things about carbon life, which I've talked about before, is we're symmetric across the center. Okay, 2 eyes, 2 nostrils, 2 teeth. No, just kidding. 2 lungs. Okay. Externally, the way we interact with our environment, we're symmetrical. Okay, symmetric. Okay, same number of teeth on the left as on the right. Okay. So the bottom line is that this symmetry is something probably based back when our DNA split, unzipped to make an RNA, and where that RNA got replicated completely. That replication is a complete complement to this side. So this would be the basis of replication, and this symmetry that we see on people and other creatures. Every life form on the planet has DNA. Every life form has symmetry. That goes a long way. And so most likely life in the universe is going to probably show something similar, but won't look anything like life here on Earth. Because the life here on Earth turned out the way it did because of all the circumstances, the actual physical circumstances Earth went through made us the way we are. See? So I don't know. I think you see my point there, guys. And Tara, I think if you have another question, I think this is probably a good time to take it because kind of stop.
Well, it's kind of along the same lines. You're talking about carbon and how things bond together. And so like isomers, if I'm pronouncing that right. So is there a preference on how they're formed? Because from what I understand, some are straight and some are bent. And the bent ones may have allowed for our DNA to form because it has to twist, where some others, the structure is flat. And what does that have to do with life, perhaps?
Yeah, and what Tara just said is very important. Okay, she talked about the geometry, the angles. That's really important. Now, an isomer is indeed a compound that has the same molecular formula, but a different structure. You can have your hand in this position. You can have your hand in this position. Okay, it's the same hand. Nothing's different. Right? Hi. Right? So really that's what this is kind of the same thing. Okay, in a sense, it's sort of an isomer.
Not to joke, but aren't some isomers left-handed and some right-handed?
Yeah, you're talking about chirality, it's called. And
you doing that with your hands made me think of that.
I know, because they use hands. I was about to say, you can't superimpose one hand on the other and get the same thing, because one's going to be outward facing, one's going to be inward facing. And no matter how you do it, you can't get them looking the same. So that's a process called chirality, where there's this asymmetry, yet we're symmetric this way in the mirror image, right? But we can't superimpose and get the same thing. But that's neither here nor there with that, but that is true, Daryl. But one of the things that you're talking about with the isomers, Tara, is very important, and that is that the flexibility of the carbon atom goes a long way to assist us. For instance, all right, these are isomers right here. These are the same molecular formula, but different structure. Now, why is it different? Notice the bromine, the Br on the first one. It says 1-bromopropane. Okay, no, this isn't an organic chemistry class, but what I'm saying is just below me right here, you see 1-bromopropane. Okay, and down by the bottom, okay, just below Tara, she has a nice grin on her face, just below the H. Okay, well, two H's to the left, you see the bromine in the lower left, right? Other side. There you go. There it is, right there. I got it. Yeah. And that's where the bromine is in this 1-bromopropane compound. To the right is 2-bromopropane. Well, it's the same compound, but it has a different structure. Same molecular formula, but look where the bromine is. It's in between the carbon atoms, not linked to the end carbon atom. Same thing, different structure. So this is an example of an isomer. Same formula, different physical structure. All right. And that's what we see a lot of. And those variations go into making a variety of different capabilities, characteristics, and give different properties to many of these compounds that are carbon based on our planet. So when you talk about the isomers, it's sometimes it's the physical structure, sometimes it's actually the geometry. Okay, and that geometry can lend itself to a different structure as well. Like when you have ammonia, you have a certain layout of the hydrogen atoms. Okay, they're spaced a certain number of degrees apart. Okay, well, you can also no matter what you do, you can't modify that. That's going to end up staying the same way. But for some more complex molecules, you can have a structure that looks like this, but then you can also make it look like, say, this. Okay, or like that. Yet it's all the same structure. It's all the same materials, just in a different angular orientation. That's how I liken some of this as well. So that's kind of how the isomer world works in a totally insufficiently explained nutshell.
Oh, so those different structures, when you're doing it, that's what gives the elements the ability to bend and fold onto themselves, is because of how they're structured like that, because they can fit into themselves in different ways.
That's kind of correct. In fact, we talk about that with cis and trans configurations. I noticed you actually had a question about cis and trans as well. You wrote, is there a preference as to how isomers bond, cis being bendy and
or trans
kind of straight? Well, it's interesting because in nature, cis bonds are generally more reactive. Okay, they can be changed more easily than the trans bonds. Okay, and trans bonds are pretty much going to stay what they are, and they don't necessarily have to stay that way. And I don't want to speak above my organic chemistry level here. Okay, but I will say that cis configurations. What does that mean? It means basically whether the molecule is like this or the molecule is like that. Same molecule, just a different angular position, right? The way things are bonded, right? Well, the cis ones, they can be affected by more things and can be changed into other things. The trans ones are kind of like straight, and they tend not to be as flexible. This, now you can understand for those out there that are wondering what trans fats are. Mm-hmm. Okay, trans fats are straight molecules like that don't have the ability to change very easily. So when you get trans fats, they're not going to go away very easily. I mean, think of it that way. So it makes it easier to understand how the cis and trans process works. Trans fats, zero trans fats. I'll eat it. If it has trans fats in it, you don't want to eat it because those are not going anywhere. They're going to stick with you for a while. So that's not healthy either. And again, I'm not a health show here with these guys, but I am just passing on some of the information that we know about those configurations. Did you have any more that you wanted to talk about?
About carbon?
Yeah.
Well,
that's fine. I just need to know.
No, I think those were my main ones right there. I might have some hidden somewhere.
Okay. Well, you go ahead and look then, and I will continue. So we talked about how the carbon atom is ubiquitous. It's everywhere. Okay. In this image here, this is an image of that we took at SkyTour West called the Dark Horse Nebula. Now you're looking here at carbon molecules for the most part, which are those black areas. Again, those aren't voids in space. That's dark, obscuring dust. And that dust because it's interstellar dust, it has a specific arrangement, specific look. Okay. And in fact, here is an image of an interstellar dust grain. Actually, this is a intrasolar system grain. It's a grain that was taken in the solar system. But you see, that's just 1 micron across. That 1 micron line shows you how big that is. So this is only a few microns long. And these are grains. These are the same kind of grains that could go into, say, being a dark nebula out in space. So when we see these things, we look at the universe, the Milky Way. You look down the Milky Way here, you don't just see stars. You see these dark, snaky lines of Milky Way. Non-Milky structure, the dark structure. And that dark structure is those dark nebulae that are so persistent in our galaxy. This photo, by the way, was taken at SkyTour West right after sunset. The Milky Way is that bright right after sunset because, look, you can still see the orange of the sunset to the right, the bottom. So if that doesn't give you an idea that you should, darn you, subscribe to SkyTour live stream and just hang out with us, okay? I don't know what does. When we look at galaxies, this is a picture of the Andromeda Galaxy taken at SkyTour Livestream West. But if you notice, in the disk of the galaxies also have these dark, amazing dark lanes of dark dust. Again, it's tempting to say dark gas and dust, but there is no dark gas. This is dust. It's dust, and usually it's carbon. Where does it come from? Well, the carbon comes from old stars. When an old star swells into a red giant, it tends to puff its outer layers off, but those outer layers are so far away from the main core of the star that those layers can actually form molecules. And sometimes you get carbon atoms that form with other carbon atoms. And now you have this beautiful little carbon molecule, and that's what you get. And that is like a soot. And that soot ends up becoming the dust of the interstellar medium. Among other things, there's other materials that make the dust as well. But for the most part, there's a lot of carbon out there. you know.
So I have a question. So when the carbon locks up with itself, it
Yes, the carbon.
when it's so it can't really. I mean, it's locked rigidly, correct? It doesn't really have the ability to rotate, from what I understand. So it's like locked in place. And is that similar to how magnets work, Mark? Like the elements inside the magnet are locked in place and flat and rigid. So do they repel like magnets do? When
That's an interesting question, because now you're coming down to what is a covalent bond, what is a ionic bond, the way chemistry works. But let's just take a look at the carbon atom from a high level. If you have one carbon atom and it bonds with the other carbon atom, it can't do this. It can't do any of this twisting against the other atom. So in effect, it is sort of locked like that. Okay. And you get a lot of those, and they tend to make these long, thin, well, you saw it. It tends to make some interstellar dust that has this kind of weird shape to it. Okay. Again, no gravity to speak of. So gravity affects the way things are shaped. So it'll tend to sit there, but they won't twist amongst them. They won't twist off each other, but they'll just move like this. Okay. And then with a lot of them, you actually can get this dust that's visible and will block the light from the distant stars. So I guess the question comes down to how those actually work together. I mean, how they connect together. Well, it is a chemical bond. It's a bond, that you've learned in chemistry. Okay. And the bonds are bonds shared by electrons in the outer shells of the carbon atoms. Okay. And when they do that, they are bonded to each other unless something comes along to separate them, like some kind of explosion, a shock wave, whatever. Maybe that can separate them. But they are going to pretty much stay the way they are, because by and large, most things out in space stay the way they are out in space. They don't change all that much, And the hard part to understand here, I think, for many people, is that there's really no discussion of temperature in space. Things in space only either absorb radiation or radiate. They don't have a temperature. You can't take the temperature of the vacuum of space. There is no vacuum temperature. There is just space. And there's only particles that could, say, capture radiation and heat up themselves, like my sweatshirt. Okay. In the sun, this will get hot. But we have air that conducts, so the air can be hot too. You can feel hot air on your face. We just live... Again, I know it's a side note from what you were talking about, Tara, but we're just so used to living under an atmosphere that we really don't understand how hostile and how stark and Spartan space is. It's not a true vacuum, but it's certainly not the same everywhere either, right? We see how the interstellar... Well, you heard when the Voyager spacecraft left the solar system, it started getting these plasma waves that were coming at it like knots, hitting the spacecraft. Well, what's that? Space isn't homogeneous. It's not the same everywhere, but it is actually quite. It is quite a. It's a rarefied environment. It's an environment where there's few molecules of anything, typically, and so. When we talk about a nebula, like when we look at the Orion Nebula and we see these dark nebulae you can't see through, right? We're seeing this black space between the stars and saying, oh, wow, look at that. We can't see the stars through them. That must be really dense. It's like a cloud. Clouds look really dense from the ground. But when you go through them in an airplane, you just go through them and you can kind of see through them, And that's how it is. That's how it is in the universe, too. These clouds are so big, light years across, So the carbon atoms bonded together will form dust. And that dust doesn't go anywhere for billions of years unless it gets absorbed and made into a planet somewhere along the way. Right?
And they just keep bonding and bonding to each other if they happen to bump into each other.
That's the key point. If they happen to bump into each other. If you have a bunch of them, then they have a mutual gravity. Their gravity is higher than the others around them, so they will tend to attract more. And guess what that makes over time? All these kind of-
Planet or
absolutely
something.
planets, yes, or stars, depending on what they're collecting. If they're collecting carbon, then maybe they'll start as a carbon core and bring in other elements in interstellar medium like magnesium and calcium and oxygen and other things like that, hydrogen, even helium. And next thing you know, if it's enough hydrogen and it gets under enough pressure and gets big enough, it becomes a star. The universe is
cool.
amazing.
That's so cool.
It is an amazing place. And, and you're an amazing audience, all of you that are listening to Sky Tour Radio tonight on the 26th of September, almost to October. On one hand, I don't like it because my summer sky goes away. But on the other hand, I like it a lot because now the winter sky is coming and we get all these new objects to check out. So I hope you guys are going to enjoy that with us. I know Daryl is going to enjoy it. I know that every time I've said to him, I said, hey, Daryl, you want to come along? I'm just going to do some testing on the telescope. He's like, holler at me when you're ready. And he's always there. Okay. Because he likes, because it's so cool. It's an amazing universe. And
I'm trying to get you to go back to Cepheus some more.
I will, actually. I want to look at the Flaming Star Nebula and other places like that.
Lots of dark nebulas in Cepheus.
Oh, yeah. You talked about the other day. And Amanda, you've got to come out with us more. I don't know where you've been. I've tried to message you a few times, and I don't know what's going on. What's happening?
I'm so far ahead of you guys, hour-wise. It used to be all right. You used to start about 9 o'clock my time, which isn't too bad, but now you start around 1 a.m. and
I totally forgot about that. Well, guess what? During the winter, it starts earlier. Like tonight it's right now it's almost 8 o'clock here. It's 5 o'clock out there. But before long, we're going to be 2 hours different. Okay, is that November, Tara? We're doing that? Yeah, we know.
Sure.
Yeah, I know you don't know because that's the joke. They don't change their clocks in Arizona. They don't change it. They're on their own time. Well, la-di-da.
It makes things easy for us. That's all I can say.
That's for sure.
We got to go, Mark.
It's easy for you. I will talk to you guys next week. Thank you, Tara. Thank you, Daryl. Thank you, Amanda. We will be back again on Sky Tour Radio. Good night, all.
Good night.
Bye.